Ice that burns? In the environments we are most familiar with, fire and ice are mutually exclusive. Standard physics dictates that fire should melt the ice, and the resulting water should smother the flame. This material occurs naturally in massive, unharvested quantities across the seabed. It is a stable, solid substance that carries its own fuel within its frozen structure. To understand how these molecules stay bound together, we must look at the unique physical environment at the bottom of the ocean. The search for this energy source begins in the open ocean, far from the reach of traditional drilling platforms. Reaching the deposits requires remotely operated vehicles built to withstand hydrostatic pressures that would crush a human diver. At the seafloor, the environment is defined by near-freezing water temperatures and intense geological activity, where vents release plumes of superheated minerals. This extreme depth and freezing temperature acts as a geological pressure cooker, creating the specific conditions necessary for this material to form. Scientists refer to this as methane hydrate. It is distinct from ordinary ice that has simply trapped gas bubbles. The gas is actually part of its crystal structure. Under deep sea pressure, water molecules snap together to form a rigid, hollow lattice known as a clathrate. Highly flammable methane molecules are forced into and locked inside the center of these molecular cages. The resulting hydrate remains stable only as long as it is kept under the freezing temperatures and high pressure of the deep sea. When brought to the surface, the cage collapses. As the ice melts, it releases the trapped methane, which provides the fuel for a continuous blue flame. These deposits are not isolated anomalies. They are distributed in massive quantities throughout the world's oceans. By mapping topographic relief, we can identify these deposits along deep oceanic trenches and continental margins. Researchers estimate that the raw energy potential trapped within these hydrates is immense, representing a significant portion of the planet's total carbon. The volume of methane trapped in these hydrates dwarfs the combined energy totals of all known coal, oil, and natural gas reserves on Earth. If harvested successfully, this reserve could provide enough energy to power the global economy for generations. Despite the scale of this resource, it remains almost entirely untapped by our current energy infrastructure. The challenge lies in extraction. The moment methane hydrate is moved from the seabed, the molecular cages begin to destabilize due to the drop in pressure. As the hydrate ascends, it melts prematurely, breaking down into violent streams of gas before it can be captured at the surface. Uncaptured methane is a potent greenhouse gas. Any failure in the extraction process poses a severe risk to the climate, as large-scale leaks would accelerate atmospheric warming. Mining this fuel requires maintaining deep-sea pressure through the entire extraction process, turning a massive resource into a high-risk engineering challenge. We are left weighing the potential of a vast new energy source against the environmental risks of its recovery. Earth hides impossible materials. To explore the science hidden beneath our feet, subscribe to The Explainer.